welcome back. Today's topic is electrostatic energy and electrostatic energy density. In the last video lecture, we have discussed about computation of electrostatic potentials for different charge configurations. And in this video lecture, we will derive an expression for electrostatic energy and electrostatic energy density. So let us take a random space where this is a random space which is represented here. And I am moving three charges Q1, Q2 and Q3 from infinity into this particular space. So I will move one by one charges. So first I will move on to Q1 from infinity to point P1, and I will move charge from Q2 to P2 and next from Q3 to P3. So what happens now is when I move this charge Q1 from infinity to this P1, P1 will be gaining a potential. So when I try to move this charge in this region now, already P1 has got a potential, right? So the impact will be there when I try to move this charge Q2. And when I move this charge Q3, then I'll be having the impacts of these 2 points on this particular point. So let's have a quick look about how these will be happening. So first of all, when I initially move this charge Q1, since there are already no charges which are present there, initially there were no charges. This is the first charge which is being brought to P1. So from infinity to P1 it is being brought. Since there is no charge already available, so there is no electric field which is already present. So initially the work done is 0. Now moving Q2 to P2, already a charge is being brought Q1 and it is at position number P1. Already Q1 is at P1, right? So now again you are moving Q2 to P2 from infinity. So in this case, there is a work done which is equal to the charge and the potential which this point is experiencing due to this charge. So I'll represent that one as V21. So W is equal to the charge into potential difference at point 2 due to charge at point 1, V21. Now, if I move Q3 to P3, already there is two charges Q1 and Q2 which are located at P1 and P2. And these will have a voltage effect on P3. So let this voltage be V32 and this is given by V3. Okay. So when I move this Q3 to P3, so it will be Q3 into V31. So I do have two potentials now. One is due to charge at Q1, the other one is due to charge at P2. Now if I add all these three, work done in moving first charge, second charge and third charge. First charge it is 0, this is second charge, this is third charge. If the works are done in reverse order, let us suppose if I bring first of all third charge. So here it will be 0, this is second charge, this is first charge. Now let us add these two charges. Let us add these two work done. What I will be getting, this is the way how I am adding these things. Okay, I'll take common things and see this V12 and V13, if I join, I'll get V1, this is V2 and this is V3. So this is WE. This is a work done in moving the charges Q1, Q2 and Q3 to the points 1 to P1, P2, P3 which are at potentials V1, V2, V3. This is the final equation for work done in moving these three charges. So if there are n charges, now the generalized expression now, half of Q into V, where V is the potential at that particular point and Q is the charge which is being moved from infinity to that particular point. Now if instead of n charges, let us suppose if there are charge distributions, and this is the way how we will be computing. So instead of directly Q into V, what I will be doing, integral of rho L into dl into V. This is for surface charge, this is for volume charge. Now, so considering this volume charge distribution by Gauss law, what we have already known, see this is what we have discussed about work done when we do have different charge distributions. Now having said that, if we consider the volume charge distribution, we have already gone through Gauss law, where this is the expression which we do have. Now if we substitute this expression in the previous one, this was the work done for volume charge distribution. So instead of rho v, I will be placing this particular del. So you know that this del dot d V is the potential, where D is the electric flux density. Now this electric flux density is a scalar, whereas electric flux density is a vector and potential is a scalar. Now we do know, you might have studied in your vector algebra that this is an identity. So assuming that A is a vector and B is a scalar, I'll use this identity now. So this particular expression now, it converts into this expression. So I'm substituting this here. Once I do this here, so this is my expression. Now the first term which I do have. So this first term, now I'm applying this del dot sum vector dv. This I'll apply divergence theorem. You know that when I apply divergence theorem, it will become just only this term with surface integral, right? So this term is basically 0 if we consider the entire surface. The potential into flux density over a continuous surface is basically 0. So I'll get this particular term, the right hand side term. Now we know that del V is nothing but your minus E. We have already done the Maxwell's second equation. So if I substitute this one, I'll be getting this half integral of D dot E. So this is the dot product of these two vectors. This is the work done. Now you know that D is already equal to epsilon E. This is what we have done in our unit number 1. So if I substitute it here, what I'll be getting? This is epsilon E square. This is the work done, or the energy which is employed for in an electric fields. And this particular equation gives the electrostatic energy. If you want electrostatic energy density, you need to do it for volume differentiation. So the energy per unit volume is given by dWe by dV. We know that already dWe is this particular equation. If I differentiate it with respect to volume, this is my expression. So this expression is called as energy density, electrostatic energy density. Okay. So I hope now you are able to develop expressions for electrostatic energy and energy density. This is a lecture level problem. Try to solve this problem, and if possible, we'll do it in the class. Thank you.